So make sure that you have the new packet. So today and on Wednesday, hopefully we'll finish it in two classes, we want to formalize some of the things you learned on Friday. Talking about failure and fracture, but the mechanics. What's exactly going on? We start with comparing ductile and brittle fractures, and then I'll teach you about the stress concentration and crack propagation, a little bit about creep and also fatigue. So let's just start here. Try to see if you can fill up these blanks from the things you learned on Friday. On Friday, I hope I convinced you that when the specimen is larger, even if from the same material, it has typically smaller tensile strengths. Remember? So we said this is the case because the same material, if it is larger, it's weaker. Why? No one remembers? What did we say? What is inside the material that when it is larger creates weak points, which makes the material less susceptible to failure? Flaws, exactly. So I showed you a small packet of candy, and I showed you how a little notch can actually make it very easily tearable. So I just realized that I didn't bring my stylus with me, so I have to use my hand. But today would be okay, unless someone has a stylus for surface drawing.
Actually, I'll do it.
Oh, 5.6 reference. I was explaining something to a student on the surface, and let's see if it works. It would make a lot of difference. Yeah, it works. So, yeah, great, thank you. I'm not used to it, but okay. So we need to acknowledge the existence of flaws within the material. Let's see if I can get this nicely written. Yeah, so I think I know what the problem is. Anyway, this word is flaws. So these flaws cause stress concentration with magnitudes that are much larger than the average stress. And that's why the larger materials are actually, the larger specimens may be even not as, yeah. I don't know exactly. I guess the movements are different between different stylus. But today we don't need much stylus. If you can accept that here, these flaws cause stress concentration with magnitudes that are much larger. So today we want to learn a little bit more about that. The first topic is to see how ductile and brittle fracture are different. We have already talked about ductility and the difference dynamic behaviors are different in these two materials. So look at your next slide and try to fill up those blanks. When you compare brittle and ductile fracture, what would be the difference in terms of plastic deformation, in terms of energy absorption, which I hope you remember has something to do with toughness. We said toughness is the area under stress-strain curve. So the tougher the material is, it deforms much more before rupture. It doesn't want to work. I'm too clumsy. We don't need it much today. So, when you were doing the quiz, I tried to practice with my finger. So, if the material is ductile, we expect to have much more plastic deformation, the wording, whatever you chose, it's okay, like larger or whatever. And then the material absorbs a lot more energy until failure. Remember the stress-strain curve. So we said here is a strain, here is a stress, and the area underneath is a strain energy. And that's how much energy the material absorbs up to a certain strain. So for a ductile material, it's much more, which also means much more toughness. And the toughness, we defined it to be this area until you have actually rupture. That means rupture at the end. And brittle is the opposite. We have little or no plastic deformation. I think I showed you the chart already a few times. When you break it, it just breaks like that. There is no warning and very little energy absorption. We compared this last time. Now, we want to look a little bit more closely. The reality is, engineering materials are not completely brittle or not very ductile. If a material is very ductile, if you stretch it, it becomes really like that. You have necking until you get to a point. You have a lot of plastic deformation. But engineering materials are not like that. This is more like gold or some very soft materials. Or if you have elevated temperatures. If you increase the temperature, some material behave like that. Think about caramel. If you just stretch caramel, if the temperature is a little bit high, you can kind of visualize something like that. Brittle, like chalk, we also don't use it for construction because it's very scary if something just breaks like that. Normally we have something in between, moderately ductile. It can be a spectrum, more like here or more like there. So, and you see that in terms of necking and rupture, it falls somehow in between the two. What happens is when you have failure, which is brittle versus ductile, it has very different characteristics. You probably have experience with brittle fracture. Have you ever seen, or maybe it's happened to you, that the bottle breaks, a beer bottle? I don't know, in Germany there was a tradition to, I don't know, throw the bottles and break them next to the river. I never understood why, but break them. And then you will see this little breakage. If you ride your bike, you'll be very sensitive to that. You see that the failure is very explosive. You see a lot of small pieces like that. if you look at a ductile failure, if you inspect it, you see that there is a lot more deformation. You don't see so many little pieces. It's not as explosive. No warning, much more warning. Now, what happens when you pull on a ductile, moderately ductile material? You have negative. If you had a way to look inside, you would see that there will be, after a while, some micro voids, some cracks. Let me increase the size a little bit. So if you now today nothing works. Okay, this is at least larger. So you see that you will have some micro cracks, micro voids here, and then after a while, these voids join together, they become larger, and then when they are very large, somehow towards the end, you see that you have shear failure to the surface. And that's why it is at 45 degrees, because it doesn't go perpendicular to the loading, it goes at 45 degrees. If you use a scanning electron microscope, SEM, and look closely at the breakage, you kind of see these little microvoids. You may be able to see. And you see this kind of cup and cone shape when you look at the fracture, just because of the mechanism that you see what is happening inside. So you kind of see how this failure has happened. So everything is different when you use your hands. Okay. Yeah, so because I use my hand to write, it doesn't use it to expand. Okay. So you see basically how a moderately ductile material would behave. What about a brittle material? Well, it will be different. If you, I don't know how easy it is to see for you, if you compare the actual surface of the moderately ductile, you see this kind of a cup and cone, but on the other side, you see that it's completely flat. This is actually one of the questions in your homework, which homework number 2. I show you a shape, and you become like a forensic engineer. So you have to say what type of failure you think it has been from the shape of the fracture, and answer a few more questions about that type of the fracture. So this is one way to find out what has actually happened. But what happens microscopically? It turns out that when we have brittle fracture, it's very different. You don't have this necking, you don't have these pores, you don't have this whole process. What you have is a weak point which very rapidly propagates. You have very rapid crack propagation. So for example here, the crack has started here, and you see this kind of V-shaped patterns pointing to that. And you see that this is a brittle fracture. And this crack, depending on the material, can have different features. Metals may look very homogeneous to you, but if you had a microscope, this is how it looks like. This is how it still looks like. If you have a not very good microscope, this is 4 millimeter, you see the so-called grains. So inside steel, there are these grains. And sometimes the grain boundaries are weaker than the grains themselves. This is common. So the crack, when it wants to propagate, it always chooses the weakest route. So it goes between the grains. And you have these intergranular cracks. If you have a little bit better microscope and you look at the crack interface, you see these nice grains, crystals, 3D at the crack surface. So that is how intergranular crack looks like. In contrast to that, we have transgranular. So here, if you look at the grains, so this is like one grain, the crack goes right inside. This is different. That means that the boundaries were very good. The grains are very well bonded to each other. So the crack prefers to propagate through the grain. And if you have a better microscope and you look at the crack surface, you see that there is no sign of those beautiful three-dimensional crystals anymore. So if you have a very different, like a rough landscape, it looks like a landscape if you compare one to the other. So these are ways that you can analyze the modes of fracture and find out what actually has happened. It turns out that materials which were ductile before, if you change the temperature, some of them, they can have a transition and become brittle. I don't know if you still remember, it's been last week, but I showed you a few scary scenarios, including some ships during World War II. I showed you some ships made of steel, which were very strong, but during the World War II, they developed all of a sudden cracks such that they broke in pieces. They became like two pieces. You see a crack in the middle in this figure. I know it's black and white and not in this figure, but you kind of see that the ship is broken. And what happened here was that the type of steel that they were using was like this pink curve. This is pink. The pink curve. Look what's happening for this pink metal. Here, the y-axis is impact energy. This is how much energy this material can absorb. We'll talk about this a little bit more later, but that's a measure of the fracture toughness, how much energy it absorbs. And here you have temperature. There are certain steels, certain metals that have this distinct shape. If you are lowering down the temperature, the amount of energy that they can absorb becomes very less. They become brittle in other words. But if the temperature is a normal temperature, everything is okay, as you can see. In the next module, you will see what this PCC means, but that's the name of the crystallization at atomic level for a steel. So what makes the difference between this metal and the other metal is really at the atomic level. This is body-centered cubic crystal, and that's face-centered cubic crystal. We will learn about it. But in the case of Liberty ships, they were using this kind of metal. They didn't know about this phenomenon, which is ductile to brittle transition. So you always have to make sure that you are above this temperature. And this is not a very low temperature. So it was only 40 degrees Fahrenheit for Liberty ships, and they had this catastrophic failure. What happens is, then when the material becomes brittle, if you have the smallest crack, it will propagate very fast, and then you have a catastrophic material. Very easy. And you see that some other materials, they are not very sensitive to temperature. When I say they are not very sensitive, it means that if I change the temperature, it doesn't change much, how much energy they can absorb, etc. And here are the examples that I just showed you. So in both cases, they were using material which would have been good in normal temperature, room temperature, but at even 40 degrees Fahrenheit, I forgot for percent what was the number, but for Liberty, this is 40, and they had this catastrophic failure. So the rule of thumb, or the advice here is, you always have to use them in situations where you are above this dB/T, which is ductile to brittle transition temperature. Any questions so far? No. Now that we kind of see what's going on, and you can even have a steel becoming brittle, we need to learn a little bit more about stress concentration and how the cracks propagate. This is the center core of fracture mechanics, which can be a graduate course on its own. So we just scratch the surface. I want to give you the basic and important ideas. So I'm happy I put this slide because everyone seems to have forgotten last week's lecture. So Da Vinci, for example, he conducted an experiment which looked really like that. He was using wires of different lengths, and he was putting stones in it, I think. And then he was measuring how much they can hold his wire. And he observed that when the wires were longer, they were different. They broke much faster at lower amount of rod. So you see that then the rod falls into this basket. This is his experiment. So we kind of know that the strength of engineering materials is much less than the perfect material. If they were very, very tiny and you had no cracks, no flaws, the material could have orders of magnitude more strength. This is what I showed you on Friday. So if you go from perfect material, the same material, to an engineering size, you may have 2-3 orders of magnitude reduction in strength. This we discussed last time. But the question is, what is happening? And you know the answer already, but we didn't know how to calculate. The answer is because flaw concentrates stress. But what does it exactly mean, the concentrated stress? It means that, let's say here, the stress, the nominal stress, the average stress, so this is average. Let's see if I can write here. So this is an average stress, sigma 0. But it turns out that if you have a flaw, so in fracture mechanics, we represent flaws with electrical penny-shaped cracks, these are called, like that. It turns out that the stress at crack tip, which is at the corner, at the sharp corner, is not equal to sigma 0 anymore. It is a multiplier by sigma 0, and this multiplier, it's called a stress concentration factor. Now see if I can write this. A stress concentration factor. It's very large, I know, but KT. So it's larger than sigma 0. And how much larger? This KT, let's change the color. You can see this in this relationship that KT is equal to 2 times square root of A over the radius of, this is a tough one, radius of curvature. And let's look at this question a little more carefully. Does it make sense? Doesn't it make sense? So this is saying that the stress here is not equal to sigma 0. It is larger. If I show you the next slide where we plot it, you see that when you compare the average to the stress at the tip, you see that it's much larger. But let's see what these parameters are. What does it mean? Does it make sense? First of all, A. Pay attention. You may have an internal crack or a surface crack. If it is the surface crack, it's just the length of it, A. If it is internal, it is kind of a diameter of this pen-shaped crack. So look at 2A and A. I hope it's shooting through and out. If you want to mark it larger, make sure you do that. So this is 2A, that's A. So this is nothing else but the size of the crack. So does it make sense? Does it make sense that when the crack is larger, we have a larger stress concentration? Yes? It makes sense. When you see a formula, it's always good to look at individual parts and try to see if it makes sense. I think it makes sense because if you have a larger crack, everything is worse. So you want to make sure that this stress concentration is proportional somewhat to this side. How about radius of curvature? If you don't remember this from calculus, it's not a problem. You can just look at the definition here. Conceptually, it is the radius of the circle that you can fit on a curve. Imagine a wheel running over a curve. That would be like the smallest. Now, does it make sense that the stress has a reciprocal relationship with the radius of curvature? What does it mean? If I consider this crack and this crack, and we are looking at the radius of this is impossible. I cannot draw this. Which one do you think is more critical for fracture? The one which is sharper or the one which is kind of has a fillet? Which one is more critical, the sharper one or the sharper one? Yes. So which one has a smaller radius of curvature? The sharper one. So it makes sense that the stress has a reciprocal relationship. If this is a small, this should be large. It all makes sense. And if you look here, you can see that when you go from average to the tip, this is how it looks like. Why do we care about that? We care about it because if you don't know, if you didn't know about this, I didn't tell you that, you will say, okay, forget about it, I don't care, this is just a small crack here, if the whole thing is large, you would design for sigma 0. But the reality is that you would have a stress that is larger than sigma n. And that would mean your design is not good. You're going to have a catastrophe in your head because it's going to fail much sooner than you think. Sigma m is typically much larger than sigma 0. So, and we need to learn how to calculate it because we want to prevent failure. So that's what we want to do. We want to know what is the maximum. And last time we did this little quiz, and we looked at these three different cases, and you can calculate again for yourself that sigma 0 is the same for all three. But here, because the radius of curvature is much smaller than here, it's going to be, the sigma m is going to be the largest. And because of that, this is going to fail. Also, sigma 0 is the same. I write it like that. It means that sigma 0 is the same for all three. It's super hard to write with the finger. Any questions about this so far? I feel like you all have too many classes before coming here. It's hard to keep you but I'm doing my best, okay? I'm doing my best to make this interesting. Okay, so the last thing before letting you go. We want to then look at a few examples and so on Wednesday to see how this translates to design and material selection and everything. But let's start from here. The rule of thumb for an engineer is avoiding any sharp corner. You don't want to have anything which is sharp. You don't want to have very sharp transitions. What you are looking here is just a graph showing if you go from one section to the other, then this can happen when you design a fillet structure. And then you see the radius of the fillet here, and the difference between the width of the upper piece and the lower piece. So you can see that this stress concentration factor, which you have to be wary about, because this controls how much larger your stress is than you think it would be. This increases when this contrast between W and H increases. When you have a big change going from one to the other. That makes sense. Also, the sharper your fillet radius is, it means that R is smaller. So R is smaller. You can see that the sharper it is, you will have more stress concentration. So if you look from here to here, it goes up like that, as it should. So the rule of thumb is you should always be wary of that. So let's just stop here.